Hello everyone, this is Piyush Raut from Electrical Engineering Department and this is DSP Lab experiment number 3. In this experiment what we are going to do is we are going to use autocorrelation function to find out the pulse rate of the given PPG signal. Before going any further, let us see what the autocorrelation function is. Autocorrelation function is given by the following formula: R of m is equals to 1 by R0 sigma n equals to 0 n minus m minus 1 x of n into x of n plus m. So what we see here is basically it is the same signal. Since it is called autocorrelation, it is the multiplication of a signal with a delayed version of itself. Here we can see, if we consider x of n plus m as the signal, then x of n is a delayed version of itself. So we are just multiplying and summing it over a window and then dividing it with r of 0. What r of 0 is, basically this is the first value of the autocorrelation function. It is also known as the energy of the signal, because when the value of m is equals to 0, we can see it is basically x of n into x of n, that is x of n square, which is also the what we say, it is also the formula for finding out the energy of a signal. So we are basically dividing it with the energy of the signal, and this is autocorrelation. So what is the use of autocorrelation? Autocorrelation basically gives you the similarity between the signals. In this case, since we are using the same signal, it gives us the similarity between the data points, as if suppose at t is equals to 0 and what other time t is equals to 5. We can see if the autocorrelation is very high, we can say that the signal is very periodic, or the same values of data points are coming up again and again. Autocorrelation is less, means that the values are very distinct and the same patterns could not be found. So autocorrelation basically is used to find the patterns in the data, and this is all about autocorrelation function. The following is the algorithm to find the pulse period of the signal. So here we are using the zero crossing point, and we'll see what the zero crossing point is in the further video. So in the first part of the signal, here we have taken a float array X, which is a PPG signal, which is about 2000 samples long and sampled at 100 Hz. So we made an array of X and stored the PPG signal into that array. So we are going to first, as per the algorithm, first we are going to run the moving average filter over this signal. So this is the code for moving average filter. We are using the length of filter to be 8 to smoothen out the signal. We are storing this resultant value into an array called y of y, and what we are going to do is we are going to find the mean of this array and subtract it as a part of normalization of the array. So here we are finding the mean and subtracting the mean from the moving average filter output and storing it into another array called x1. Now we define the autocorrelation function. We are using two for loops, and as per the autocorrelation function's formula, we are just multiplying and adding those values and then storing it into the ith position of an array called autocorrelation function. ACF of I, we are storing the value r. Now according to the formula, we need to divide the whole array by the first element of the ACF, that is the energy of the signal. And so we stored the value of ACF of 0 in a variable called t, and we are dividing each element of the array with this variable t. Now we have to implement a zero crossing point using the following logic. What we are saying is, if the value of ACF of I is less than 0 for a certain I and is greater than 0 for for the consecutive value, then it means that the function has gone through from a positive to negative change or a negative to positive change, and hence it must have crossed a 0 point. So whenever it is happening, we are storing that value and breaking the loop. So we are storing it into a integer called ZCP to find out the zero crossing point. Now what we are going to do is, according to the autocorrelation function, the first peak after the zero crossing point, we need to find the distance to this peak. So we are initializing two variables, that is Lmax and max dash to both to 0, and we are iterating from the indices greater than ZCP but less than n and incrementing it every time. And if we are finding that if max dash is less than ACF of I, then we are changing the value of max dash to ACF of I and Lmax to I. Every time this is going to run, we are going to find the first peak after the zero crossing point, and we are storing it. Now, in order to calculate the pulse or the period, here we are finding the distance Lmax1 as Lmax plus Z zero crossing point, and the period is Lmax1 by 100, it is 100 milliseconds. Now the pulse is defined as 60 upon the period because it is 60 seconds per period. So this is the formula. So we are printing this pulse and we are plotting all the arrays to see how the output waveforms look like. So let us see on the serial plotter how the waveforms look like. So here we can see the blue one is the original input signal, the PPG signal. We ran a moving average filter of length 8 over this, and this the red one is the smoothened signal. This is the smoothened signal minus the mean, and the yellow one is the autocorrelation function. We can see this is a nice reducing peaks of reducing intensity, and this will go up to 2000 samples. In order to find the pulse rate, let us just comment this code and run the code again. Let us check on the serial monitor what the pulse rate is. Here we can see that it is coming out to be 58.25. Generally, it has to be in the range of 50 to 80. So we are getting about 58.25. So in the second part of the experiment, we are expected to find the pulse from a voice signal which we recorded using the software. So this X array is the voice signal recorded at the rate of 8000 samples per second. So this is the X array. We stored it into a float array, and these are the 1000 samples. We are using the same code to find the moving average filter, the autocorrelation function, and all the outputs. So using the same code, we are just we will first see the waveforms, and let us see the serial plotter. So here you can see that this is the original voice signal, this is the moving average filter, this is the moving average filter minus the mean of the signal, and this is the autocorrelation function. So we obtained the nice graphs of all the signals. In order to calculate the pulse, we will just comment this code out and uncomment this code and upload it to the board. Let us see on the serial monitor. So here we can see it has to be in the range of 85 to 180 for adult male. It is coming out to be 98.77.